So welcome at this year's Student Best Paper Award presentations. We are recording these talks for others to watch, so if you have any questions, you will have to say them to the microphone. As I am doing it now, I will be handing it out during the Q&A. We have three speakers this year, Tomáš Winter, who already presented, Michaela Urbanovská, and Zdeněk Rosypálek. Each of them will have 20 minutes to present their talk, their paper, and then 10 minutes for Q&A. At the end of these presentations, you as the audience will also get a chance to vote. I will send a link to the seminar Slack and show the QR at the end for you to participate as well, and we will take it into consideration while making the decision of who will win the 1,000 euro, which is the prize money for this competition. The winner announcement will be done during the barbecue, which is exactly in 1 week. We hope that the winner can be here. We will see about that, but that's an occasion where most of you will be attending, so there will be audience for this nice little ceremony. Today, Stefan will be the host of this session. He, as you have noticed already, he will be asking the tough questions during the Q&A, and that's it from me. And we can continue with our second speaker, Michaela Urbanovská.
Okay, I hope you can hear me. Yeah, I can hear me, so you can hear me. Hopefully you can also see me. Great. So first of all, thank you all for coming. I'm very happy to see so many people here. I never had a chance to present this work. So today, gracefully, I present to you the neural networks for model-free and scale-free automated planning, which was actually my first PhD journal paper that I wrote with my supervisor. I was the first author, of course. And it was released in 2021 in the Knowledge and Information Systems, which is a Springer journal. So that's the theory. And now let's look at the long and not very catchy name, right? I was never very good at naming papers. It's a bit sad, but it's true. So it has a lot of parts. First part, we have the neural networks, which you probably have heard of. They're pretty, well known around here. Then we have the model-free and scale-free, which, model is kind of a cursed word in the AI in general because everyone uses it for something different, and I find it very frustrating. And then we have the automated planning, which is a bit too big. So we're just going to focus on the classical planning, which is what we mostly used in this work. And why did we even do that? Well, the thing is that a couple years back, people started noticing that maybe using all of these separate methods and separate fields is not the optimal thing to do. Maybe sometimes you want to just mush the things together and they can do something great. And recently, it's been a thing with more symbolic approaches and more statistical approaches, such as the classical planning and neural networks, to make some step towards general AI, which you all know Terminators. I don't think I have to go there. Now, let's start off with the classical planning, because I feel like we all kind of know what neural networks are about, but classical planning is the thing that people find sometimes a little bit boring. But it solves problems. What a surprise. You have probably heard that 1,000 times if you know me. And the problems have to be deterministic. So every time you take an action, you know what action it is, you know what's going to happen, and it's 100%. So if I decide I'm going to take a step to the left, I do, and voila, I'm here. Now, the problems are also fully observable. So I know for a fact that there's not a hole next to me, so I can make the step to the left. And those are just two of the properties of the problems. There are a couple more that are way less fun to animate. So, for example, they also have to be discrete. So these are just nice pictures, but in reality, you would be making like small actions, step by step. And there are many different things you can use in the classical planning to solve these problems. And there are the more fun ones, the domain-independent approaches, which I think are better, because honestly, yeah, they are. Because you can use the same algorithm to play a Tetris game. You can use it to plan your day, or to deliver your package in the best way, or to solve a maze or something. It's exciting. And then we have the domain-specific ones, which are a bit less exciting, because you use them only for one thing. But the fun thing about them is that they're really good. So, like, if you have a domain-specific solver for these labyrinths or something, like, they're going to be fast. So it's kind of, depends on what you want. If you want something very universal, you're going the left way, the domain-independent planning. And we're kind of somewhere in the middle. But I like to talk about this more as, like, kind of steering towards the domain-independent approaches. Now, this is how the pipeline works. So you have a problem. We all have one. And now maybe you ask yourself, okay, so we have all these beautiful domain-independent things. Like, how do we use it? I want to do it. Well, that's the catch. There's always a catch. And the catch here is you have to model the problem, because you cannot just, sit next to your solver and be like, hey guy, like I got a problem, help me solve it. Cannot do that. So you have to sit down, usually, make yourself a nice cup of tea, and model your problem. Which sucks, to be quite honest, because it's a lot of work. And people are trying to kind of go past that, because it's not fun work. But once you do it, you can throw it in your solver full of those beautiful domain-independent things, and then you have a solution. So this is what it's all about. And the problem modeling, as I said, is a bit annoying. Here you can see it live, as I was coding it yesterday for you. And the problem contains two different parts. So when you want to solve something, you don't want to look at it as like an actual real world. Like, I don't want to be solving my teeny ass problem in this like universe. No, let's make it smaller. So you define yourself a world that is big enough to contain your problem, but small enough that it's, it doesn't contain any unnecessary information. So for example, if I have the warehouse and I have some trucks and some people and some other things, packages, carts, then I can say, okay, so this is my world for warehouses and trucks and people and packages, and I can load stuff. I know a lot of actions these things can do, so I define my actions, I know what's in the world, and I know their relations, and I know their different properties, so I can say, okay, this package is heavy, and then no, this one is not, that one actually is light. And then you can say, okay, so this person can only pick up light packages, and stuff like that. So you basically define everything as possible, and then you have to focus on your actual problem. So that's what we call the problem description, or the problem definition, where you have initial state. That is basically your situation. You're just describing what's happening at the moment. And then your goal condition, which is what you want to be fulfilled at the end of this beautiful planning journey. So in terms of the packages, your goal is probably not going to be related to every single thing that's in the world, right? It's probably just going to be, that's my package, deliver it to my home, and I don't care about the rest. So that's what's your goal condition. And now if you have these, you can get into planning. So this may look like a big skip, right? Like there should be a slide in between, but now it's fine. So at the left side, you can see the initial state. So let's say I have two warehouses, I have some people, some trucks. The screen is very tiny, but we have the initial state. This is where we are, this is what we want to solve. And now you can do actions. You define them, you model them. Okay, so I can load things, I can walk somewhere, I can do stuff. And that creates many different situations, or as we call them, states. So if I go ahead and I load a package to a truck, the package is no longer on the ground. So I'm in a new state where the package is somewhere else. And this is how you create a state space, which is this magnificent graph. And this is a tiny one, so you can probably somehow intuitively tell that these get big. And when they get big and you want to get to your solution, it takes time. And there are many different ways to do it. You can go blindly, you can just, try, and usually that's not a very good thing to do. Or you can get help, and that help is called a heuristic function, which you're probably also familiar with, also used in many different contexts. But a heuristic function looks at your options and says, okay, well, I think this situation is a lot better than this situation, so maybe you should, go that way. And that's exactly what we want to improve. So what can we learn here? These things are so nice and like fundamental. Maybe we can add some machine learning to it, right, as you do these days. So the first thing we want to learn is the state transition function. Maybe I don't want to sit all day and model my actions and, like look at the warehouse and just pinpoint everything that's happening. That sounds like a bit of a stretch. Like, who's going to pay for that? So maybe we just want to make this a bit more automatic. And the same thing with the heuristic function. These are usually done by hand, by features that people extract from the problems, from the structures. Again, a lot of work. And also, humans, like, they're not very perfect. They don't see everything. So maybe if we have a different set of eyes, like a neural network with 0 eyes, it could see something else in the problem than we do. So those are the two things that we want to improve and replace. Not the planning as a whole, but the two parts that we thought make sense. So the first thing was done by something we call the expansion network. So instead of modeling all the actions and writing them down, we have something that is going to just look at the warehouse. For example, you could say camera. We're not quite there, but you could say camera. That's just going to, look at the warehouse, note some actions, and know what's going on, and then send it to the solver. Now with the heuristic, it's very similar. You can use something, you can use computer vision, you can use some other detective methods, and you can get some features that are going to help compute the heuristic, or just, do the heuristic as a whole. Now, that was planning. And now let's get to the second part, which is the model-free and scale-free property. That sounds a bit like, what is it? But we spoke about the model here for a bit and how annoying it is. So it's probably no surprise that we want to go model-free now and get rid of the modeling bottleneck. That is not easy to do because people love their standardized planning language, but we tried to do it in a little bit more neural network friendly representation. So we started using grids and image-like structures, as we like to call them, in order to get rid of this. And then we wanted to extract the information from those grids. Now that is, I think, pretty clear. You want to take the most annoying thing out of the equation. That makes sense. And then we have the scale-free property, which is even more important. And that is, we don't want to solve only one side of the problem. That is usually an issue with neural networks, that the input has to be fixed and the output has to be fixed. And there's a lot of, like constrictions. But we want to get rid of that. We just want to take one neural network and feed any grid into it, basically. So that was another goal that we had. Now, just to show you what was the database for this, we were using 4 domains with like increasing difficulty. They're not very difficult. We're actually working with a bit more difficult ones, except for Sokoban. That's the most difficult. But those are the domains we have. So we have different variations on mazes. You have one agent, more goals, more agents, more goals. You can see the increasing complexity, I think. And then we have a Sokoban, which I can never tell if people are actually familiar with it or not. So I'm going to quickly tell you that it is a puzzle game, a very old one, where you have a guy who pushes boxes onto goal positions. And that's basically it. And the catch is that you can push the boxes into dead ends very often. So it's pretty difficult. And those are all domains. And now, you cannot really just put this nice picture into a neural network, can you? So just to give you an idea of the encoding we were using, you can see that every one of these grid cells has 4 values on it, which means, you just put the one-hot encoding where the object is. So if there's an agent on the grid, you're going to put the one in the 3rd position. Very simple encoding that I think we kind of used to this day. And now let's get to the neural networks. I'm not going to go into like the fundamental theory of the training. I think most of us heard it a million times. And also you can read it in the paper. But this was the first architecture, the expansion network. And here's kind of like showing you what do you want to replace with what. So at the top, you can see the transition function, which is what is essentially used in these like search algorithms. And that usually gives you like multiple different states you can add up in. So again, I'm standing on a place. I can do a step forward. I'm going to have one state. I can go to the left. I get another state. You get the gist. And this is kind of not what we want, because generating sequences like that is not that simple. So we wanted to make it more probabilistic. So what we want after our network is to give us a probability of which you can end up somewhere. So here we can see that the agent is at the bottom left corner. So it can clearly do only 2 actions. So it doesn't matter which one like it picks, but you know that the top one can be chosen with 50% probability. Same thing at the bottom. So you're going to have 50% nothing and 50% agent. And that is essentially what we wanted to learn for the transitions. Now this is how the architecture looks like. I'm not going to go over that step by step. I just really like this picture, so I wanted to show you. And you can see that it's just a very simple convolutional neural network. There's nothing very complicated to it, and that's usually the goal of all of our architectures, that we don't want it to be like some super huge black boxy neural network. That's usually not our goal. We're trying to go the other way. So this is the architecture. And here's the result. If you want to go into the metrics later, I can explain, but I don't think I have a lot of time for that. But we were actually able to train one network for all the mazes. Not the Sokoban, that's a whole different story. But for all the mazes, we were able to use one network, which was very nice. And it was not really surprising because the rules of the movement are very similar. So we were actually able to train that and use that later in our planning algorithm. The Sokoban was a bit complicated. Again, I can get into it later, but it turned out that it's not as simple as it looks. So we were not successful there. That was the sad story. But now let's get to the more fun stories, which are about the heuristic network. So essentially, again, those are the input-output examples. So you want to give it a state, and back you want a number. That's going to tell you, okay, you're this far from the goal. That's good. So for the first one, we know there are 3 steps to the goal. The second one, we know there are 6. The problem is that these numbers are optimal, so it's really hard to get them. actually as hard as solving the problem, which doesn't help you. And heuristics should help you. So what we wanted to do was to create some architectures that are going to give you like a different estimate. So we started off with this one, which if you look very closely, you can see it's almost the same as the previous one, which is on purpose because we were lazy. But we actually realized that it's not a bad architecture at all as a baseline because it's quite simple, it's quite fast to evaluate, and it's always nice to have like a fast, simple baseline. So this is where we started with just a simple convolutional network that is then flattening some of its like large tensors inside into one vector, which is kind of like a neat trick to make it scale free. And then on the output you have one value, which is telling you the value of the heuristic. The second network was a little bit wilder, and we came up something that's called the attention block. Attention was all the rage back then, so we needed it. And what we did was the most important thing are these red layers over there, the attention masks, where you actually made the neural network take a look at your maze, and it was like, oh yeah, this looks interesting, that there's an agent. And then another layer told you, oh, this also looks kind of interesting, there's a goal. So you had like a whole bunch of these layers that were telling you different interesting things you should draw your attention to when computing the heuristic. So that was the main thought here. And then the recurrent neural network was very difficult to draw. So there's like a very general scheme, but it was very similar to like LSTM and stuff like that. The most interesting thing here is the self-stopping module, which kind of worked, but I thought it's a very fun idea to make a network learn when it should stop itself. So that was the third architecture. Now each of them was kind of inspired by something. So the first one was mostly just a baseline for like image processing, because that's what we were essentially trying to do, because papers at the time were using that. So we wanted to go that way. Then we had the attention one, which does something that is called landmarking in planning. I mean, it didn't do it precisely, but it reminded us of that. So we thought it's a good idea. That it's looking for the interesting parts in the problem, the interesting parts of the grid and stuff. And then the recurrent one, we kind of hope is just going to kind of learn to solve the problem itself. That's not really happening, but this one was actually very helpful because to this day we are using recurrent neural networks. Not this one, but the principle was very important at the end. Now, the loss function I wanted to mention because it's like the most awesome piece of math in this paper, but I don't want to go over that because it's just, you can read about it, it's fun. But I just wanted to show you what's the thought about, because very often in papers in this field, you see that people are just trying to get as close as possible to the optimal values. So if I have like the truth values, the y vector, where you say, okay, the first sample has 4 steps to the goal, the second one has 2, and the third one has 3. Well, that's what I want to learn, right? 4, 2, 3. Well, the thing is not really, because you can then learn something like 4, 5, 8, and it's going to be completely useless. So what we did was focusing, instead of on the actual values, on the relationships between the values. Because you don't care if the first one is 4 or if it's like 15. What matters that it's the largest number in the vector. So you know it's the furthest from the goal. And it doesn't really matter like how you say it, It's far. So you want to know that it's the largest one. And this is at the very end of the loss function being circled around and around. And those columns and rows are actually telling you relationships between the values in those vectors. So where the zeros are, everything is fine, which true. The 10 is the largest, the 4 is the largest, those are good. The problem comes in the second and the third one, right, where you kind of want to switch the order, and that's what the 3s do. It's a bit more complicated than that, but it's telling you how much you should skew these values in order to get the right order you want. So if I now took a 3 and added it to the 5, I would have my perfect order, and that is exactly what we wanted. So the planning experiments are like the largest part here. We did a lot of it because we wanted to show not only we can do this, like we can train this, but we can use it in these algorithms. So we did use the greedy best first search, which is using only the heuristic to navigate, because it is, very important to know that those heuristic networks don't have any guarantees. So we just wanted to use something very simple. We trained everything we could, and then we tested it on unseen problems, big problems with some time limits and metrics. And here's a large, large table of results, which are very interesting, but it would take another 20 minutes. So the most positive results we got from this were that we were actually able to do the scale-free models. We had the expansion network that was very reliable for 3 of the 4 domains, which was great. And there was a very clear ability to generalize on larger things. So if you look at the first table, you can see that the coverage, which is how many problems were actually solved, is actually pretty high, even like on the very large instances, like 64 by 64. So those were kind of promising results for like the first time trying this stuff. And then the limitations were clearly that using the network for the expansion is pretty slowing down the search because you use it a lot. So we actually in the future kind of stopped doing that and only focused on the heuristic. And another one was the time information trade-off, because even though we thought that the attention heuristic is going to be very good, it actually turned out that it's taken so long to compute that it doesn't even have time to shine. So those are mostly the results we got. And what's the biggest contribution? Well, I think, personally, that the biggest contribution is that this is like my largest paper on my PhD. And this whole work is the reason why I'm even standing here right now. And also, which is even more important, that we're still doing this. We're still learning heuristics. We're improving very successfully. And yeah, so I think this was like a first step back at the time in this journey over here that I think was pretty important and essential. And it showed us what not to do. So yeah, thank you very much for listening to me. And I hope you like the pictures.
Okay, so thank you very much for the talk. I hope that we can hear and it's also recorded. So first, the audience, do you have questions to Misha? Okay, so let me start as a planning expert a bit cruel. So you say that you are domain independent, but at the end you are dealing with mazes and Sokoban. Is there anything to see where these ideas generalize?
It is. It is. At my current work, actually. Because as I said, we continued. This is what we started with because of the similarities in the domains. So we wanted to see if there is some like relation between these very similar domains, which there was. And then we started expanding into still grid-based domains, but very different ones. Because these have something that we like to call locality. So you have an agent that is moving, so everything is kind of based around that one tile where you know the agent is. But there are many problems that don't have this very property, and this is what we're trying to explore now, if this actually works for places where you don't have the agent. And now we're going even a bit further, and we're trying to detect these grids and things where they're really not. So we're taking like different planning problems that don't have the grid inherently in, and we're trying to find it and like kind of abuse the structure still, even though it's not there like on the first sight. So yeah, they are kind of generalizing pretty well.
Okay. Yeah, wait.
You need a mic.
And you were saying that there was a time minute limit for something that was testing, and during training, how are the
No,
timings?
that
Like
was
how
during
long they were
the
training steps, or
I don't remember the full on details, but I remember there was like 500,000 samples for training. I think it was something couple thousand epochs, if I'm not mistaken. And the 10-minute time limit was actually for the planning problems. So because these tend to be quite large, there's usually like a set time limit per one instance. So it was 10 minutes per instance, which is like quite harsh compared to like other competitions, but you know, deadlines, so you cannot do long times. But yeah, and the training was actually fairly fast, I would say. Like it was like within hours it was done. The worst one was I think the recurrent network. That one was really, because I think it didn't run on GPU as the only one, so that was like a tough one to train in practice. But still, it was like in matters of like days. I think it was done like 2 days, and you have a network trained.
and another question is like, when you were doing the trainings, the variability, right? It was like huge, or it was like converging nicely. How was the?
The convergence was actually pretty good, and it's very related to the loss function. Because we were also the activations did play part in that. I remember when we were doing the networks, but the most important thing at the end was really the relation between those values. But what was also important, and I don't think I mentioned that, is that the batching for the training was done in like a very particular way. So we had to, because if you just throw like a bunch of different absolutely unrelated instances on the neural network, tell it some numbers, and then you're like, okay, this one is smaller than this one. Like you just gotta know that. It's a bit unintuitive. So what we did was that we did every batch only had states from the same instance. So you would have the same maze, but with a different agent placement. And that way in every batch you would get like related basically states. So it worked. Like I don't know how to explain it other than it was just very intuitive for the neural network to learn that more than just some random states. But that is like the biggest hack we had to do there to really make it work.
Another question. It's so when you were doing the maze and you were training, the goal was changing, or the maze have fixed goal?
It was every batch had fixed goal and different agent placements.
Different badges, different goals.
Yes, because yeah, like then every batch different goal and like different agent placements, but same walls, same goal, different agents, basically. Yeah. Because if you change the goal, you change the problem. So that's
Thank you very much.
Okay. No, you can.
Thanks. So, to be honest, maybe I just didn't understand it correctly, but how did you get rid of the modeling or like your problem modeling? Because in the first place, you show us the PDDL description. And then you are using, you are pretty much like hashing your problem into like, let's say, whatever binary or description that actually like heavily uses the structure of the environment. And the neural network, again, is like, you show us like convolutional neural network, which actually, again, heavily uses the structure of the problem, that it allows you to plan in different directions, and you have just only 4 directions. So how this would scale to 3D, three-dimensional planning? Like imagine just Sokoban in 3D, or not Sokoban, but but this in 3D. Or if I would just take the problem and hash it into one single line, and then use like the convolution in single line, then I don't see how this scales, or how did you get rid of that modeling? Because I still can see it, you just hash it. So
yeah, well the thing is we wanted to get rid of it's a bit more like complex problem that has multiple different stages. This was just like a stage 0.1. But the way we got rid of it was that we were trying to use just the graphic input, which is essentially just hashing. But the thing is that you just put PDDL out of the equation, because parsing PDDL with a neural network is not fun. It's like pretty much impossible to do. There are ways to do it now, but back then there were like no ways to do it. So we thought, okay, maybe if we can like extract this, even from the PDDL, which we are doing now, we weren't doing it back then. But if you can extract this, and then you can use it like more easily, because the network sees the structure. If you give it a PDDL, the chances are it's not going to really see the structure as clearly. So we tried even that. Like we tried the one line. We tried like a 1-by-1 convolution. We called it LoopNet. It was really stupid. But we did all of that, and now we are in a place where we are working on tensors. We're working on different 3D things. So this didn't scale. It didn't. That's why we don't use the convolutions anymore. That's why we are working with like a different structures right now. And no, this did not scale very well. It did scale to like larger, but still the same problems, but with some issues, of course, because that's a common thing to do for heuristics.
and how much does it help that you have like in these type of mazes you have like 4 actions? Like this is so similar to the convolution neural network that.
That's exactly why we thought it worked the best, because it was exactly that. That's how we did the expansion network, because you can see the full, movement possibilities of the agent, we kind of exploited that. That was like the thing. But with the heuristic, it's different. I don't know which one you were referring to now, but the expansion network, that was the whole thing of it, that you can basically see all the options where the agent is moving. So we wanted to see if the network actually like is capable of locating the agents, and then the 4 spots around it. Because at first it seemed like weird that it couldn't do it, and then we actually had to figure out how to do it. But with a heuristic, it is a little bit. With a heuristic, it's a little bit different, because there the convolution doesn't really help, because it's not capable of like propagating the information through the thing, because it's pretty large. That's why it doesn't scale. So we just have to use different methods now. Not sure if I'm answering the question correctly.
Oh, okay, thanks. And one more thing is that you showed this, I think it was the attention model, like 2 slides back or something like that.
Yeah.
So more, yeah, this one. So the attention masks are like hand tuned, or it just learned it?
They learned. Those are learned.
It learned, and so you visualize them, and then you saw that it probably
Yes.
represent this type of behavior.
There was a lot of, there was like a certain number of the masks where they like stopped being beneficial and they started repeating themselves if it was like too many. So there was like always some kind of a threshold, when after that it was just too much computation. It wasn't very beneficial. But when we were actually looking at them, like you could see that the goal and the agent were pretty common. And then in the Sokoban, it was interesting because it was looking at the goals and the boxes, but like not right at that tile, but kind of around them. Like, okay, this is a box, but it was usually like, okay, you should like move it to this side. Like it was more highlighted on one side of the box, for example. So it was a bit, it wasn't like fully like you look at it and you interpret everything you see, but there were patterns definitely in these like trained. Yeah, those were just done by the neural networks as well. So you would take the input, run it through a neural network, and you would get one attention mask, and you would do this many times.
Okay, thanks.
Thank you for the question.
There was one question in the back, and I think it has to be the last one since we are over time.
We can talk about the coffee machine.
Okay, and if I may ask for short answers as well.
Okay, I'll try.
So it seems like a fairly heavyweight approach. So I was just wondering, like in terms of computational intensity and that sort of thing, how it compares to traditional methods.
That was, I'm not sure if it's very visible from the tables, but yeah, exactly. The most heavy thing there was actually the expansion network, because it was prolonging the time of the computation so much, it became pretty much like unusable on the larger instances. I'm kind of sad that we never did measurements without that one. I think I have them somewhere, but we never like did that part of the experiments in this work, which is kind of a shame, because I think the heuristics could have been way better without that one. But in terms of the heuristics, there are actually many ones in classical planning that are like super hard to compute, because planning is like NP complete, if I'm not mistaken. So it all is like a very difficult thing. So it depends. Like sometimes it is a little bit too heavy duty for the small problems, but then as you go bigger, it can be actually faster than some like state-of-the-art heuristics. Yeah, and also this was our first approach, so it was very like brute force.
He's nodding.
Thank you.